Hi there, I have a nice finite sum problem for you, and let's see how we can do it. So basically I have binomial coefficients, and so I can just try to, also I have the sum, so I can just try to make this whole thing look like expansion of something to the power of n, because it would look like this. I can also combine this in the binomial part, because this would mean like it's in the form of x minus y to the n. But this term is not so nice. So let's first separate this one and see what can I do with this one. Okay, so I will say it's just same for this stuff. I will keep them because they're not a problem. But this one, I need to do something about it. So I want to get, let's separate this thing a bit further. X minus y to the n, so it will look in this form. So basically, if this thing was also like in the form of x to the n, it would be nice. Well, this is actually look like an integral of, so imagine if I had x to the 2k plus 1 over 2k plus 1 at 1 and 0, this would just be 1 minus that. So it would be equal to this thing. And this is integral of x to the 2n. So let's just delete this thing and say this is x to the 2k. Wait, let me also put the integral. So it's from 0 to 1, x to the 2k dx. Of course, it's dx because we got it by power rule, not k. Okay, so now I have an integral and also a sum, and they're both finite, and both of these functions are just continuous. There is no problem in it. So I can just swap them. There's nothing required for that. So from 0 to 1, and then I get the sum. K is from 0 to n. So I have this thing, minus 1 to the k, n chooses k, and this thing, x to the 2k. And this whole thing is just dx. Okay, cool. And now, so what is this sum part? Did I manage to make it binomial form? So I have n chooses k, so this means I have nth power. And I have x to the 2k, not just x to the k. So this, I have to treat this like x to the 2 to the power of k. So this is x squared. And I also put minus because I have minus 1 to the k. And I don't have any other term that got the power n. So this is just minus 1. Sorry, it's just 1 minus x squared to the n dx. So now this integral looks simple, but it's a bit lengthy actually. Now we will make a substitution and see, this is very famous integral. So let's put x is equal to, I can put sine or cosine, they will basically be the same thing. Let's put cosine. So what will this integral be? Wait, also let's say cosine t. It doesn't matter, but anyways. So when I put x is 0, this is pi over 2. And when I put x is 1, this is 0. And I will also get a minus from dx. dx is going to be minus sine t dt. So I can just swap the bounds, and I will also get rid of the minus. So it's from 0 to pi over 2. 1 minus cosine squared, which is sine squared. Sine squared. And I also have the nth power, sine 2n t. And also I have this thing, sine t dt, so it will actually be 2n plus 1 dt. Okay, so this is actually called Wallis integral. If I pronounce it wrong, Wallis integral. And so, well, yeah, there you can just find this solution everywhere. Let's try to do it quickly. So instead of just solving for to the power of 2n plus 1, I will just show you the recurrence relation for I when it's just power n. Okay, and then we can just put n plus 1. So we're solving for the general case. So sine n t dt. Let's solve this one from 0 to pi over 2. Okay. Well, we have few options. I can separate one of the signs or two of the signs, or just don't separate anything and try to do integration by parts. Well, first and third options doesn't work well, so I'm gonna do the second one. So I'm gonna say this thing is just so I'm gonna separate two of them, and so it will be sine n minus 2 and sine squared, and sine squared is 1 minus cosine squared t dt. And now I'm just gonna separate the sum, and it will be 0 to pi over 2. So this is sine n minus 2. Also, let's remember this. So this is just sine to the n, okay? Sine n minus 2, and I have minus sine to the n minus 2 times t cosine t. I have dt, it's not so important. Sine t and cosine squared t dt. Okay. And this is also, of course, from 0 to pi over 2. So the way the reason I said it's recurrence, because so instead of just calling this thing I, well, it actually also depends on t, because for different t's I can get different t's, so I can a different answer. So I can say this integral, instead of I can just say in. So this I also depends on n. And now the reason I said this, because this thing has the power of n minus 2, so this thing is actually just equal to I n minus 2. So I already got rid of this term. I mean, I know it. And then I have minus this stuff. So let's try to do this thing. And we will do this integration by parts. So let's use tabular method. Let's just call this I2. Or if I say, okay, I will just call this I. We didn't use I for something else. And to integrate this, well, I can just take sine n minus 2 for derivative. But if I take one of the cosine and try to integrate it, it will actually be something simple. Sine n minus 2 and cosine x. 2t cosine t. Because if I call sine t as x, cosine t dt will just be the derivative of that. So this will be very simple. And what I'm left is just cosine t. So derivative is minus sine t. And this integral, so if I call sine t as u, this is just u to the n minus 2 du. So this will just be sine to the, I'm increasing the top by 1, dividing by the top, n minus 1 t. Okay, it's this simple. And okay, so now I just do plus minus. So these two minuses will become a plus. So this I integral will be cosine t times this, cosine t sine to the n minus 1 t over n minus 1 plus, so it will be minus minus plus the integral from 0 to pi over 2. Also, this thing is from pi over 2 to 0, of course. Pi over 2, 0. So this will be n minus 1 times 1. So this will just be sine to the n. And I'm just going to have a 1 over n plus 1. Sine to the nt. So again, this thing is just in. We call this thing in. And if I look at this thing, well, when I put pi over 2, cosine will be 0. And when I put 0, sine will be 0. So this thing is just 0. So this I is going to be equal to just 1 over n plus 1 in. So it's just in over n plus 1. So let's go back here and substitute it. So I said in is equal to in minus 2 plus this thing. So let's just put it here. In is in minus 2. Did I get a minus? I have the minus here. So I have minus I. Minus 1 in over n plus 1. Okay, cool. So now let's just solve for in. And I'm going to get in is going to be in over in minus 2 over, so this is 1 plus 1 over 1 plus n plus 1. I think I made a mistake here. this was m minus 1. Yeah, okay. So this is m minus 1. This is also m minus 1. Okay, cool. M minus 1. So this will be n, m minus 1 over n minus 1 over n, I, n minus 2. So this is a nice, easy recurrence. And it's very easy because it's just multiplied. I'm just getting the new term by multiplying the two previous term by something. Okay? And, well, I needed I to n plus 1. So here, well, actually, to solve this thing, we can't solve directly in. We need to also separate it for m to n plus 1 and to n for even and odd. We can just solve for the odd one, and they're just same logic. Okay? So if I put n is equal to 2n plus 1 here, I'm going to get 2n over 2n plus 1. And this will be just 2i 2n minus 1. So it's just like decreasing this thing by 2 and you get this constants. I can just do it again. I can just keep doing it. So when I put n is equal to n minus 1 here, I'm going to get 2n minus 1 on this side. So it will be this thing. And this will be so this will just go one more less, because I will also get the multiplication of 2n when I put n minus 1 here. It will be 2n minus 2 over 2n plus 1. And also when I put n is equal to n minus 1 here, I will get 2n minus 1. So this will be 2 less, 2n minus 3. Okay, so I can just keep doing this. Till which point I can go? Well, these are all odd numbers, all of these n's. So I can go up to I1. So I can go up to I1. Let's put it first. And so when I have minus 3 on this side, this is minus 2, which is 1 more than that. So when I have I1 here, this will just go down up to 2. So it will be 2n minus 2 up to 2 over, well, this is just same. All of these are just 1 more than this. So it will be 2n plus 1, 2n minus 1 up to top 3. But it's same as saying just 1 because these are all even numbers and these are all odd numbers. Well, I can just write it like in factorial form too, but I will just use double factorials. It's easier. So 2n double factorial means just go, instead of just going 1 down on each step, just go 2 down. So this is equal to that, and this is equal to this. 2n plus 1 double factorial times I1. So I also need the first one. Well, I1 is very easy. So what did I say? In is just signed to the n. So I1 will be the integral from 0 to pi over 2. Well, I'm just going to put n is equal to 1 is sine x dx, which is minus cosine x pi over 2 and 0. So this is 0. When I put 0, it's 1 minus 1. This is just 1. So I1 is 1. Well, so then I don't even need this thing. Okay. So I solved for sine 2n plus 1. So what did I do? I first expressed it in terms of this in integral. Then I solved the general form. I found the recurrence relationship for in. And then I said, well, I can't just solve it for in, but I can do for even or odd ones. I needed just the odd ones. So I solved for this. So this will be my answer. Let's just go and put it back there. So my answer was just going to be I of 2n plus 1. Answer is I of 2n plus 1. Which is, so I said just it's 2n double factorial over 2n plus 1. Double factorial. And that's the end of it.